It's from Hrithik Pandey, and he's going to talk to us about the development and validation of object detection algorithm for a robust video-based laser safety system.
Hello, everyone. Thank you so much for allowing me to present here the work that I have been doing. It's a laser safety system algorithm for detection of aircraft for optical and thermal infrared cameras. And we want to look into the current state and result. So today we'll be looking into the overview of the algorithm, and then we'll also look into the data we have collected from different sensors. Then we'll look into some examples, detection examples, and some data we have analyzed, the distribution, and then we'll also look into some special cases and along with some final conclusion. So for background, for all the SLR observations, we use class 4 laser, which has power between 0.8 to 1.4 watt. And especially if we do debris tracking, we need even more powerful lasers. So if we are going with higher power laser, it is our duty to go with, to avoid minimal, to reduce the risk of exposure. And hence, we are working on this part of laser safety system. And the algorithm, the developed algorithm is very simple. It has just 4 steps. In the first step, it takes the raw image and it performs the edge detection. And after the edge detection, the bin approach, where the image is segregated into bins of any size, depends on the requirement or the resolution. And then a standard deviation for each bin is calculated. And the threshold is set, taking the standard deviation and calculating the mean of the standard deviation. And this highlights the bin containing object in the image. And then we can apply contour detection to calculate, to locate the center of the bin, or locate the position of the object present inside the image. In this slide, I want to show what is going on in the back end of the slide and every step. So we have raw image, and the red box we see here is actually, there is an aircraft on the image. People cannot see in the back, so that's why I highlighted with the red box. So after edge detection, it highlights there is an object. We can see the edges of the object. And then we apply the binning, and now the bin which contains the object gets highlighted, and then using the thresholding and contour detection, we can locate the final position of the object inside the image. Also, for image, so when you are doing real-time operations, we don't want our laser to switch off anything even detected near the edges of the image. So we define critical circle, and it is like any object detected within the circle will trigger the alarm to switch off the laser. And if it is outside the circle, of course, there is no need to worry about it. And this radius of the critical circle depends on the field of view. So in our case, the camera has a pretty narrow field of view, and hence we chose to go with entire width for thermal infrared and entire height for the visible camera. And also it depends on the performance, how fast the algorithm is. So all these factors determine the field of view, the critical zone of the image. The data we collected from 2 cameras, one thermal infrared camera, which is VarioCam HD 600, and we collected 20,000 images with field of view. It has a field of view of 6 horizontal versus 11 degree in vertical. And the other one is Oh, there's something wrong with the bullet. The other one is visible wavelength, which is RZ178 mm. And for that also we captured 20,000 images. It has a field of view of 9 degree in horizontal and 5 degree in vertical. We also recorded corresponding ADS-B data, so for the cross comparison, and the data recorded during day and night. The weather conditions were clear. We also recorded some other data, around 78,000 images, but they were under cloudy and hazy conditions, and hence for this particular analysis, we only are going with the clear sky conditions. These are some examples when we found an object in the image which had no ADS-B call sign. And especially this object is very peculiar because it looks like a parachute with a cargo with it attached to it. This is a thermal infrared image, and we have corresponding object located in the image. This is in visible wavelength, and we have successful detection here. And please note this object is not present on the ADS-B. This is a special case when the aircraft is flying in front of the clouds, and our algorithm has managed to detect aircraft even in that condition. This image is from thermal infrared wavelength though. Coming to the analysis part. So for daytime in thermal infrared, when we compared based on the ADS-B, there was a potential aircraft, there are potential 14 aircraft should be present in the vicinity. And out of 14, all 14 got detected from thermal infrared camera. And it is important that aircraft which has length less than 34 meters are detected up to 22 kilometers distance at elevation of 20 degrees. And for on the right, the distribution is for the visible wavelength camera. And based on the ADS-B, there was 10 potential aircraft. Out of that, 9 got detected from the visible wavelength. And even in visible wavelength, we had detection of the small aircraft even at low elevation. But please note those aircraft which are at low elevation are very close by, at a distance of 5 kilometers. Now, looking into the one missed opportunity for the visible camera, and when we looked into the data, we found out that the camera at that time was pointing very close to the sun, and hence the image was very overexposed for visible wavelength, and hence we have this one missed opportunity for visible camera. For the nighttime data, in the left for thermal infrared, there were potential 21 aircraft based on ADS-B, and out of that 19 has been detected. And in the nighttime majority, all the aircraft, most of the aircraft detected has elevation above 20 degree. There are few aircraft again detected at low elevations, but the distance is quite low. They are less than 10 kilometer distance. And on the right for RZ camera, out of 24, 19 got detected. And it has even a similar distribution as IR camera. Those which are detected at lower elevations below 20 degrees are not too far from the sensor, and hence even managed to capture at low elevation. Looking at the missed opportunities for thermal infrared, there are two missed opportunities. When we looked into the image, we found those aircraft are at very low elevation and at a distance of around 32 kilometers. The other one is at a 26 kilometers. And if we look at the corresponding image, we barely can spot aircraft in the image. And there is actually aircraft, but this is where if you pay real close attention, and hence the algorithm could not identify the aircraft in the image. For the RZ camera, we have a same trend. Aircraft has low elevation and distance is quite high, except for one situation where aircraft is above 20 degree and distance of just 13 kilometers. Still, it is not detected, and it is because in the night time, the RZ camera only depends on the blinking of the light, aircraft light, and sometimes when aircraft is very nearby, they fly really fast, and it gets difficult for the camera to capture the aircraft when it is going really fast, and maybe because of that, we could not detect the aircraft which was at 21 elevation, but was very close by. So if we summarize the result from Infratech, we had overall detection percentage is around 94.2%, but if we consider detection above 20-degree elevation, we have 100% detection. For RZ camera, daytime, we have only 90% detection, and for the nighttime, that percentage dropped even further to 80%. And for aircraft above 20-degree elevation, the detection probability is even 95%. So I want to talk about, even though RZ camera has performed not as good as thermal infrared, but if we look in this situation, there is a thermal infrared image with, we can see only one aircraft, but at the same time, we captured visible wavelength image, and there is one more aircraft present in the back, which is where we can see the condensation trail. So one of the, one camera, IR camera detected the nearby aircraft, whereas the visible camera only detected the far aircraft. So we can say that if we use the combination of two, it can provide a very good coverage of the sky. In conclusion, the algorithm works really well for the thermal infrared. IR camera has some shortcomings, but if the combination of both can be really, can provide very good coverage for both day and nighttime operations. And if aircraft flying above 20-degree elevation, it has very high chance of getting detected. Yep, and maybe we are planning to do cross comparison between the camera, visible and thermal infrared in the future, and have some more data collection near aircraft, so near airports, to have low flying, fast moving aircraft and push the boundaries of the algorithm to see how quick it is. That's it. Thank you. Any questions?
Thank you very much. Would anyone like to ask a question?
Hello, thanks for a good presentation. I wonder, when you measure with the infrared camera, did you have variations on the direction up in the air where you measured, like towards the sun or away from the sun, because the sunlight could affect your measurements quite a bit?
So we were actually just looking in the sky. If there's any aircraft, we were just directly pointing it. So it was not like we were just focusing in particular region. We were just like covering entire sky.
Okay, so that could be interesting to see if the IR results vary from where you look at it with respect to the sun.
Yeah.
So when looking towards the sun, away from the sun.
Yeah, generally we try to avoid hitting the sun, and for IR, it's good that we can go very close. As long as we don't have sun in the frame, is fine. But for visible camera, it gets overexposed even if you are in the vicinity of the sun. So that's the benefit of IR camera. That's why we could see the aircraft in IR, but we could not see the aircraft in visible when we go very near the sun. So
Okay.
that's the good thing with IR.
Okay, we have an online question. Frank Lemoyne asks, how well would your system work on drones?
So unfortunately, we could not test it with drones because we didn't have the opportunity to capture it. But we do have some, like I showed, it's a parachute kind of thing. We also have some images with balloon, and so
it would trigger a detection, I think, wouldn't it? Yeah, very good. Any last question?
Just looking at the table that you showed, you've got the percentage of successful detections, but what does that mean? Does that mean false positives, true negatives? Do you know what I mean? You have to break those up somehow.
So when it's successful detection, I mentioned like if all the aircraft, number of aircraft I mentioned is based on the potential aircraft based on ADS-B. So how we do it, like we have the mount where we are looking in the sky, and then we know the camera field of view, and we just, with that, we look into ADS-B data if there is anything at that time present in the database. And if there is something, we consider it that there is an aircraft in the vicinity, and then we do the detection. So this is how we have done, but yeah, if you ask about the false positive, based on the data I have done, we have not seen anything yet, but yeah. About that, we are still more analysis yet to be done for that.
Okay. Thank you very much for your talk. Thank you. Well, that concludes our session. Thank you to all the contributors. I'd like to thank my co-chair for stepping in at such short notice as well. Thank you.